Right, so for example 10, we're going to do another example where we're going through and we're looking for our inverse normal values. So the normal model N 500, 100. Again, we're looking for a distribution of the SAT scores for college-bound females in 2012. So first thing I'm going to do is I'm going to go ahead and label my curve here. All right, so 500, standard deviation is 100. We just did a bunch of examples using this because it's nice, easy numbers to work with. All right. All right, so in this particular case, we're asked to find the SAT score of the 25th percentile, find the SAT score of the 75th percentile, because what we're looking for is our interquartile range. And if we go back to previous chapters, remember our interquartile range is going to be our middle 50%, right, between our 25th percentile and our 75th percentile. So in my picture, right, I'm basically shading in, right, approximately this middle 50%. Right. Again, where you kind of draw your limits on your picture may be slightly different, but we're kind of looking just at this middle portion. So that's what I'm going to shade in here. Okay. All right, so there's our sketch of our curve. So now we're going to find our z-scores for our 25th percentile and 75th percentile from our table. All right, our 25th percentile, remember we want something that's going to be close to 0.2500, and our 75th percentile is going to be something that's close to 0.7500. Right, so we have two different z-scores that we're looking for. All right, 0.2500. That's going to be on our negative side because we're less than half. And if we start looking in here, 0.2500, we've got 0.2514, 0.2483. Technically that is a tiny bit closer decimal wise. So here is our 0.2514. That is in our row that starts with negative 0.6. And if we go up this column ends in 7. So we are going to get a z-score of negative 0.67. Right? And both of these are going to come from our estimations in our table. Right, now we want to get something that's as close to 0.7500 as we can. So we flip our table over. We're looking for 0.7500. We see 0.7486, 0.7517. Again, this is just a tiny bit closer. We go over this way, we have 0.6, and if we go up, we get 0.07. So our z-scores happen to be opposites, which in a way should make sense because both of them are 25% away from the middle, right? So we're going the same distance away, just one to the positive side and one to the negative side. Right? So now we want to convert these z-scores to units. So here we're going to use our mu plus z sigma. And the way I have this kind of separated, I have the notation showing that we're coming from both the 25 and the 75 here. So our mu and sigma, mu is our mean, which is still 500. Our sigma is our standard deviation, which is 100. So for our z equals the 25th percentile, we got the negative 0.67. So we have 500 plus negative 0.67 times 100, which is going to give us 500 minus 67, which is going to be 433. And then we're going to take 500 plus our positive 0.67 times 100. We're going to get 500 plus 67 is going to give us 567. All right, find the interquartile range for the SAT scores. Our interquartile range, remember, is Q3, which is 75%, right, minus Q1, which is 25%. So we're going to take 567 minus 433, and that's going to give us 134. And then to finish this off, we're asked, is the IQR larger or smaller than 1 standard deviation? Our IQR equals 134 points. Our standard deviation right, that's sigma. That was 100 points. Right. Is the IQR larger or smaller? Right, this is larger. 134 points is larger than 100 points. So the range of the middle 50% of the data is larger than just one individual standard deviation. So again, another case where we're finding our inverse normal values. This one is kind of set up as a between problem. We were looking specifically for our interquartile range, so we're using 25% and 75%.